where to put the feet, and what they want to compute is how the robot is moving from the beginning to the last position of the step. So you have on this first equation, what you want to compute is instantaneous ZMP, and on the right side is the condition at the end of the step. So RF is final ZMP where you want to put the feet, and the other parameters are the position of center of mass and the velocity of the center of mass, which they can measure. And omega and alpha are parameters they are going to optimize in order to reach the kind of walking they want. Alpha is going to optimize the period step of the robot, and omega is going to optimize the height of the center of mass and the length of the step. So for my problem, I inverse this equation because I already know how the user is moving. I know its position and center of mass, and what I want to know is where I have to put its feet in order to maintain the stability. So I inverse the equation, and now I have the final ZMP, RF, which I want to compute, and it's depending on the initial parameters of the user tracked motion that I can measure, so the ZMP, the position and velocity of center of mass, and alpha and omega are still the variable I'm going to optimize to reach that solution. So doing so, I maintain the same dynamic and same problem as for the robotic field, so I can use the same solver as them, and the difference is how I'm going to constrain and tune my physical problem. So here is a little picture to show how I'm doing. So I have to move the right foot. So I'm looking for a solution under a short range, short length range. So I'm saying, can you find a solution for that short length? If it does, then I'm moving the foot at that position, and if it can't, I'm increasing the range of the step. I'm saying, try to find a solution for a longer step. And I'm doing this iteratively until I find a solution, or until the system says I can't reach farther. I'm doing the biggest steps as I can, and yet I can't find a stable position. So in that case, since we are in animation and we still have a floating base system, we are cheating on a quick period of time to reach the closest and best solution as we can, in order to increase the stability of the system and say, okay, on this step we can't maintain the stability, but on the next step we will try to reach a better stability. So a last picture on the working pattern generator on how I'm moving the legs. With the previous method, I'm showing how I'm moving. I'm computing the final position of the foot, and now I'm showing how I'm computing the full trajectory of the foot over a step. So here I'm using an Hermite function. It's a polynomial equation to go from the initial position and velocity to the final position and velocity we desire, and doing so only with the tracked motion information, the position of the center of mass and the velocity of the center of mass. We can compute the full foot trajectory to follow the user. So the application and results. Here's the first application. I have a user with full body tracked sensors. The upper body is used for the method I explained previously, and the lower body is used to qualitatively compare the results. The position of the main limbs, so the hand, the head, the waist, and the legs, are input for a kinematic chain, and when those main limbs are moving, the full kinematic tree is moving, and it's moving the rest of the limb, like the elbow or the knee, which are forced to follow the main limbs. And all those positions are input in the simulated avatar with a floating waist, and all these positions are forced onto the avatar, which with a PD control to follow all those positions. So here is the method to quantify how I quantify the results. I didn't quantify the feedback of the user perception of how he's perceiving the difference between the legs movement or sorry, how he's quantify the difference between the legs movement or if he's feeling sickness, but instead I'm quantifying the position of the ZMP of the user and the position of the contact inside the simulation. So you have on the left an example of a plot where in yellow you have the position of the ZMP, which is quantified directly on the user depending on its position and acceleration, and on blue and red you have the limits of the edge of the support poly area of the contact area to see if the system is stable at each instant or not. The next application, we changed the sensors, so we have Vive tracker sensors. We have a real-time application, so I forget to mention on the previous application, the data of the motion capture is saved on the computer, and then it's reused later offline, but it's used in a way that the information are sent like it was a real-time simulation. So here it's directly real-time application with the computer running at the same time as the sensors tracking. And we wanted to show the application with a complex environment because we had feedback as why are you trying to generate legs movement if you already have sensors on the lower body. So here is an example of the situation. You have a bench which is obstructing the lower body sensors, and you need to generate the leg trajectory if you want to have a movement all the time. And the different kind of application are a walker with a tool bench manipulating some tools, or a fire walker applying some first aid to a mannequin. And all this information will later be studied and evaluated by doctors or medicine or ergonomics study. For the perspective and the future works, what we want to do is to quantify the difference between the avatar legs position and the user legs position, and to quantify the perception of the users of this difference. Is it important for him that the legs are really close from its own legs, or can he still manipulating without breaking the sensation of immersion? And another part is that we want to have a full consistency of the avatar, so get rid of the floating base avatar and never cheat on the system, so that if we can obtain that physical consistency, we'll be able to compute the torques and strength of the avatar, and that will give even more information for ergonomic study or for to quantify the exhausting if the task is exhausting or not for a worker. Thank you everyone for your attention. If you have a question, I'll try to answer my best. Here's a final video you can watch during the question, which will present the different movement and application I had with my control. Thank you everybody.
And thank you for your talk. My question may be answered by this video, I guess we'll see, but is this purely for bipedal sort of linear motion, or can you handle sidestepping or other types of motion with this model?
Okay, we can maintain sidestep walking with this model. Yes, it's part of the solution, but in that kind of application, the step may be smaller because the support area is wider on the x-axis to walking forward, and not on the wide.
Thank you. Thank you.
Thank you for your question.
I take on. Hi, thank you for the talk. This is super interesting and very useful, I think, for a lot of people. My question would be about the measurement you assessed your or you qualified your motion with, and the curve you showed basically, as I understood you measured the difference in positions. Is that correct? So yeah, so this COP is the difference between the real position and the rendered position, so to say.
What I quantify here is I check if the position of the ZMP, or yes, here in the plot it's COP, so since it's a flat ground, they have the same position. So what I want to check is the yellow trajectory between the blue and the red ones, which mean it is inside the contact area or not.
Okay, and have you checked something like rhythm and timing? Because I think this is also probably very important in walking. It's like the time you set off your foot and the time you arrive at your foot.
Yeah, that was on one of my first locomotion algorithm. I had the variable alpha, which was a constant, because it was the beginning, and the first feedback I had from user was the stepping is at the same frequency all the time, so it doesn't feel natural to walk. So with alpha, which is now a variable, I have a variable time step. So depending on if the step is of the stability and of the velocity of the user, I will have different time periods and different length steps, so it feels more human-like for the user. And it's quite complicated because in robotic, all the algorithms are like, we have one constant periodic time for the step, and it's quite complicated to find an algorithm with variable step for robots, because robots they don't care if it stays the same.
Any other questions?
Thank you for your question.
I have one question. So, is there any limitation of the variable controller that must be provided, or so in the second slide, use variable controller for the real-time simulation, and do you have a specific number of variable controller that must be given, or?
Sorry, which slide?
So you have a two experiment.
Yeah.
Motion capture, and then next one is using variable controller.
Okay.
Do you have a specific requirement for the number of controller, or?
For the number of sensors?
Yeah, number of sensors.
Okay,
yeah.
okay, sorry. What we wanted is to maintain the most important sensors for users, so it can maintain the immersive sensation. So the hands and the head are the most important one, because if you have differences, a big difference between the user hand and the avatar head, and all the head position of the user and the head position of the avatar, you break immediately the sensation of immersion. So those three are the most important one, and we added the one on the waist, but you could add it on the torso, on the torso, to be more precise on the position of the user.
So the minimum can be 2?
The minimum would be 3 if you add the headsets, and 4 is the easiest one to implement.
Okay, so what can be the actual minimum that can work in the extreme?
You could do 3
3
if you have the head,
okay.
because you can have an interpolation to, if you know where is the head, then you can know where is the rest of the body.
Okay, great. Any other questions? The author has some announcement. Yeah.
Yeah, good day, I'm Anton. I'm one of the demo chairs. Just a quick announcement that if you are in the fast forward session that happens at 4:30, please come at least 10 minutes earlier so that we have you set up. Otherwise, all good.
Let's thank to the speaker.